Bismillah ar-Rahman ar-Rahim. Today we'll talk about chapter 4, which is harmonic analysis. Harmonic analysis is a process of calculating the magnitude and the phase angle of fundamental and higher order harmonic of a periodic waveform. So we like to calculate the magnitude and the angle. The resulting series is known as Fourier series. We say that the function is a periodic if there is positive number t such that x of t plus nt will be equal to x of t. Like this waveform or this function over here, it is a periodic function. Fourier series of a periodic function can be written as A0, where A0 will be the DC component, plus AN cosine n omega t plus Bn sine n omega t. So this is how can we write any waveform as a Fourier series. Fourier series also can be written as the following, and this one we call it polar form. So it will be equal to C0 plus, again, a summation of Cn sine n omega t plus phi plus an angle, where Cn will be the magnitude. So it is the a square plus b square, where a square will be, or a and b will be the rectangle coefficient of the series, and the angle will be tan inverse of the imaginary part over the real part. And of course C0, again, it will be the DC component. Therefore, for a given periodic function, the constant coefficient can be derived by simple mathematical manipulation, where the DC component, which represents the area under the curve from 0 to t, and that will be equal to the integration of the function from 0 to t, multiplied by 1 over t. And the component an can be obtained by multiplying the function times cosine and omega t and taking the integration for one full period. Multiply that one by 2 over t. And the coefficient Bn also can be obtained by multiplying the function times sine and then taking the integration and multiply that one by 2 over t. We can also do some simplification in case if the wave is symmetry. For example, over here, such kind of function, we call it to be odd function. Why we call it odd function? Since x of t will be equal to minus x of minus t. So if x of t is equal to minus x of minus t, then such waveform we call it odd function. And in odd function, we're gonna have only the sine term. So only those terms will be available, only the sine term or Bn term. Okay, so this one will be odd function, since again x of t is equal to minus x of minus t. And in odd function, we have only the sine term. We don't have any cosine term. That means an will be equal to 0. Okay, this function, we call it even function. again when we draw it, of course, when it has to be through 0, of course. Okay, so again, if we draw this function, if we have such kind of function, we're gonna find that x of t will be equal to x of minus t, so they will have the same magnitude. So in this case we call the function to be even function, and in even function we're going to have only cosine term. That means only an will be available, bn will be 0. Okay, these are also some example of odd function. Okay, so we can see that around 0 x of t will be equal to minus x of t minus. Okay, so all those we call it odd function, and all those will be also even function. So again, in odd function we have only a sine term, and even function we have only cosine term. Okay, how about if we have such kind of function? Of course, this is not odd function, it is not even function, but if we look at the value of the function, for example, at x equal to t1, and then we compare it with the value of the function over here at x equal to minus t1, of course the value will not be the same. It will have completely two different values. Okay, therefore we cannot call it we cannot call it odd function. Also we cannot call it, of course, even function. But we'll notice that it has what we call it half wave symmetry. Okay, it has half wave, or we call it, so such kind of function we call it half wave symmetry, or we call it also mirror, and it will satisfy this equation over here. So x of t will be equal to minus x of t plus t over 2. So if it satisfies this equation over here, we call it half wave symmetry function. And in the half wave symmetry function, the even harmonic of the sine and of the cosine will be 0. So we're going to have only odd harmonic. We have only odd harmonic. Therefore, if we like to calculate an, we're going to have only the odd harmonic. The even harmonic will be 0. Same thing with bn, the even harmonic will be 0. This kind of function we call it a repetitive on half cycle function. It repeats itself every t over 2, or every half of the period. The function repeats itself. So in that case we'll find that also x of t will be equal to x of t plus t over 2. So in that case, in this case, we call it repetitive. And over here we're gonna have that odd harmonic will be 0 for both sine and for cosine term. Okay, so we're gonna have that odd harmonic will be equal to 0 for both sine and cosine. Let us take this example. So over here we have this kind of function from 0 to t over 2, it will be 4, and then from t over 2 to t the value will be 0, then it will repeat itself. And now we like to do Fourier series. We like to obtain the or we like to perform the Fourier series for this function, then what we have to do, first of all, we have to obtain the DC component. So how can we obtain the DC component, or we call it A naught? So we take the function and then we find the area under the curve by integration. Okay, so we take the one full period and then we take the integration, we find the result, and the value will be 2. So the average value of this function will be equal to 2. Now we like to find the an term. So this is the equation for the an term. So 2 over t from 0 to t over 2. The function is 4. We multiply it by cosine. If we take the integration, we find that an will be 0. Now let us find bn. So we take the function multiplied by sine. We're going to end up with this equation, and in this equation say that the value of bn will be 0 for even harmonic, and the value of the function will be 8 over m pi for the odd harmonic. Therefore, Fourier series can be written as x of t will be 2 plus 8 over pi sine omega t plus 1 over third sine 3 omega t, and so on. So we have only odd harmonic for sine, for the sine. The odd harmonic for the cosine term is or R0. Okay. We can do the same thing by using MATLAB. So I guess we need to generate such kind of waveform in MATLAB. We can use Simulink, and then and over there we can do also Fourier analysis, and this one will be the result. So the fundamental component or the DC component will be 2. The fundamental component will be around 2.5 as it is shown over here. So 8 over pi, it's around 2.5 something. And then this is the third harmonic. So this is the fundamental, this is the third, fifth, and so on. Okay, so this is the Fourier analysis, and we find that the total harmonic distortion will be that value. That will be the DC component again. That is the peak value for that waveform, 2.54. If we like to find the root mean square, that will be the root mean square. And then those are all harmonics. So DC will have a value of 2, fundamental over the first harmonic 2.5, second harmonic will be 0, third harmonic will be 0.84. So it has no even component. The even component for this function are 0. Now let us take this kind of waveform. So over here we find that x of t will be equal to minus of x of t plus t over 2. So this one. So this one again, it is half wave symmetry. This waveform is half wave symmetry. And then we can do the, if we like to do the Fourier analysis, of course the DC component will be 0 since the positive and the negative are identical. And since it is half wave symmetry, so all even harmonic in the function, all even harmonic will be 0. Okay, so only we're gonna have the odd harmonic for both the cosine term and for the sine term. Okay, so if we find the an for the cosine term, again we take the function, we multiply it by cosine, and this one will be the result. That will be the result of an. Of course, this is only applied for the odd. For the even are 0. If we like to obtain also the bn term, take the function, multiply it by sign, and again this one will be the result. So the for the odd harmonic we're going to have a value, but for even the value will be 0. Therefore this one will be Fourier series for this kind of waveform. Okay, how about if we look at this one? Of course this is an odd function, right? Since x of t is equal to minus x of t. Okay, so we're gonna have only sine term. So from this one we're gonna have only sine term, right? But also at the same time, since x of t will be equal to minus x of t plus t over 2, then it is also half wave symmetry. And in half wave symmetry, we know that the even harmonic are 0. The even harmonic will be 0. Okay, so because it is odd function, we have only sine term. Because we have half wave symmetry, even harmonic are 0. So a in 0, b in for the even will be 0. So we're going to have only b in for the odd harmonic. Okay, and this is an example, another example for the waveform. So again over here we have the this is odd function, since again x of t will be equal to x of t will be equal to minus x of minus t. So since x of t will be equal to minus x of minus t, so it is what? It is odd function. In odd function we can have only the sine terms. Okay, and it is also half wave symmetry. Again x of t will be equal to, since x of t will be equal to minus x of t plus t over 2, so it is half wave symmetry. Since it is half wave symmetry, then all even harmonic are 0. Okay, even harmonic are 0. So n is 0, since only we have sine term. bn will be 0 for the even, but for the odd of course it will be there. So we take the function, we multiply it by sine omega t, and that will give us the final value, and those are the result. So that will be the fundamental component. Okay, the third harmonic 0, the fifth will be equal to that, and so on. Thank you. So that's all for the